Assalamualaikum dear viewers, Shoaib and Dayo is here, and today's lecture is totally related to the magnetic circuits. And before to start the concepts regarding the magnetic circuits, we have to know about the magnetic field. So what is the magnetic field? A magnetic field can be defined as it is the area or the region around a magnet in which the magnetic poles are experiences the force of attraction or the repulsion, so that is called as magnetic field. So if we are just discuss some properties of the electromagnets, like your magnets, like your each and every magnet has two poles, the north pole and the south pole, and the two poles means if both are the same one, means the same poles are repelled to each other, means N to N poles are repelled to each other, and N to S means they are the opposite poles or unlike poles are attracted to each other. And the magnetic lines of the forces starts from the north pole and terminates at the south pole inside the magnet. And the magnetic lines of the forces never intersect to each other, and if we are moving towards the magnet, then obviously magnetic field will be the strengthened one, our magnetizing effect will be the maximum one, and if we are going away from the magnet, then what happened, our magnetic field will be in the decreasing form. So this was the little bit concept regarding the magnetic field. Now we have to discuss about the magnetic circuit. So what is the magnetic circuit? You can see from the board the closed path, as you can see, this is the circuit of the magnetic circuit we have drawn on the board. The closed path, followed by the magnetic flux in the magnetic circuit. So before that, what is the magnetic flux? Magnetic flux is the magnetic lines of the forces, which is produced by some magnetic source, that is called as the magnetic flux, and the magnetic flux unit is Weber. And what about the magnetic flux density? If we have like an area, particular area in which the magnetic lines of the forces are they have a travel, and then what happened, they have covered some area and passes through a unit area, so that will be called the magnetic flux density, and flux density, and its unit is the Weber per meter square, because here the area has been considered. So the closed path by which the magnetic flux is like that will be called as the magnetic circuit. For example, if this one is the closed path. Now in the magnetic circuit, it made up of the ferromagnetic material, because the ferromagnetic material has the low reluctance path and they have the high permeability. Permeability means it is to be provides a setup of the magnetic flux, and then reluctance, it has the low, means in the magnetic circuit the reluctance is low, because it is the position offered by the your lines to the magnetic lines of the circuit, magnetic lines, so that this will be called the reluctance, and that opposition is to that magnetic lines is the reluctance, or in the case of the electrical circuit it will be called as the resistance. So a magnetic circuit is usually consists of the material having the high permeability, like your soft steel, iron. So these are all the ferromagnetic materials which has the high permeability. It is because of these materials offer very small opposition to the flow of the magnetic flux. Obviously, if they have the low reluctance, they have offered a small amount of the resistance or opposition to that magnetic flux, which is to be set up in the magnetic core of the circuits, and then it is the electrical current is passes through a wire, which is the number of the turns wound over the material. As you can see, this is the magnetic material, and on which that we are wound some turns of the wire. So that your electrical current is totally depend, or magnetomotive force is totally depend upon the number of the turns of the wire which is to be wound on the core or the magnetic material. Okay, so consider this a magnetic circuit. Okay, and it has the closed path. Okay, which has the n number of the turns. As you can see, the number of the turns of the wire has been shown, wound on a core. When current is I is passed through the coil, if you are supplying the current which is given to that coil, okay, then what happened? The magnetic flux is set up in the core. If these windings are to be energized from the supply, what happened? The magnetic flux is to be established or set up in the core, and what happened? The flux follows the path A, B, C, D and A. So that will be called as the closed magnetic circuit, in which the magnetic flux followed a path of that closed. So that will be called the magnetic circuit. So this magnetic path which is to be followed by the magnetic flux is totally depend upon your number of the turns of the wire and amount of the current which is to be flow from the wire. So that will be called as a magnetomotive force. If we can define the MMF in the circuit, magnetomotive force, so it can be defined as the product of the number of the turns of the coil and the amount of the current which is flowing from the your wires of the coil. So this will be called as the magnetomotive force. If we are talking about the unit of that MMF, then N is the number of the turns of the wire. You can say that the turns, and what is the unit of the current? I, which is the ampere. So its unit, MMF unit, is the ampere turns. So let's discuss the flux density in the material, which is your phi divided by A, your magnetic flux, which is per unit area. So that will be called the magnetic flux density. Okay, and what about the magnetic flux? Phi can be represented as the directly proportional to the MMF and inversely proportional with the reluctance. Obviously, if the reluctance is maximum, flux will be minimum, because reluctance is the opposition offered by the magnetic circuit to the flow of the, or to the flux which is set up in the core. So if there is an opposition greater, obviously the strength of the magnetic flux will be lower one. So both have the inverse relationship to each other. So what is the MMF? If we can define the MMF over here, it is the magnetic pressure which set up or taints the magnetic flux which is set up in the magnetic circuit. So MMF is totally depend upon the number of the turns of the coil, a wound on the core, and your amount of the current which is to be flowing from that wire. So amount of the current is to be determined by the supply. If you are given the supply, obviously if with the more supply we are given, obviously the current will be more flowing from the circuit, and even though the load which is connected with the magnetic circuit, if it is to be drawn by the circuit, obviously the load current will be more, and your MMF means your number of the turns of the wire which is multiplied with the current. So it has the product of the N multiplied by I, so that will be called the MMF magnetomotive force. Second is the reluctance. So in the case of the electrical circuits, we have the resistance which is the opposition offered by the electrical circuit, the flow of current, and here is the reluctance. It is the opposition that a magnetic circuits offer to the magnetic flux. Okay, so here is the opposition to the flow of the to the magnetic flux which is set up in the magnetic core. So that will be called as the reluctance. So reluctance, it has the according to the law of resistance, it has the direct relationship with the length of the wire and inversely proportional with the cross-sectional area of the wire. So here mu naught and mu r are the your parameters which we have including in this, means your permeability of the free space and relative permeability of the magnetic material is total depend upon the magnetic material. Like your soft steel has different relative permeability, and your iron and different ferromagnetic materials have the different relative permeability values. And permeability of the free space is the 4 pi into 10 to the power minus 7 Henry per meter is the constant value. Okay, so magnetic circuits are made of such materials like your iron, steel have the lower reluctance because the value of the mu r is very large. If we have the larger value of the relative permeability, obviously the permeability means there will be the permission to the flow of a permission which is to be set up of the magnetic flux in the core. So if will be greater one, obviously reluctance will be minimum one, because it has the inverse relationship of that magnetomotive force and your reluctance, which is the opposition to that flux which is produced in the or set up in the core. Second, third one is your permeance. It is the reciprocal of the reluctance. If the reluctance is the opposition, permeance is that the permission. Okay, so that it is the measure of the ease of the magnetic flux which can pass through the material. Means if magnetic flux is set up in the core, it will be greater one, means the permeance will be more, reluctance will be lesser one. So reluctance is that opposition and permeance is that setup of the flux, which is the ease that it can be easily set up in that magnetic material. So it totally depends upon the relative permeability of the material and also your permeance and also your magnetomotive force. Okay, so here permeance has the inverse relationship with the reluctance, and if we can reverse the formula, like here A mu naught mu r divided by L, so this will be the formula for calculating the permeance in the magnetic circuit. So we are going to little bit talk about that comparison of the electrical circuit and the magnetic circuit. So first point is that closed path for magnetic flux, that is called as magnetic circuit, and closed path for the flowing of the electrical current, that is called the electric circuit. Okay, so this is the main resembling. Okay, the flux phi in the magnetic circuit is the ratio of that MMF divided by reluctance. So here current is that MMF is totally analogous to the EMF and reluctance is the resistance. So your current I will be the ratio of that E divided by R. Okay, V divided by R. MMF is the ampere turns and EMF in the analogous to that your in the electrical circuit volts. Okay, reluctance is that L divided by A mu naught mu R, or in the case of the resistance it is the L divided by A. It is according to the law of resistance, it has the direct relationship with the length of the conductor and inversely proportional to the cross sectional area of the conductor. Okay, flux density in the magnetic material B, it has like your what is the flux density? Magnetic lines of the forces passes through a unit area is that will be set up in the magnetic circuit, that is called as the your magnetic flux density, Weber per meter square phi divided by A. And in the electrical circuit there is a current density A divided by M square. Okay, MMF drop in the circuit, which is the flux multiplied by the reluctance over here. Reluctance is denoted as the S over here. So voltage drop in the electrical circuit will be like your IR. Okay, IR is the volt drop. MMF in the your MMF drop in the magnetic circuit is your flux multiplied by the reluctance. And at the last, permeance, if in the case of your magnetic circuit, is the permit to set up the flux in the core, and here in the electrical circuit there is a conductance, means it is the conductance is the opposite to that resistance in the circuit, and permeance is totally opposite to that reluctance in the circuit. So dear viewers, this was the concept regarding the magnetic circuits that we have discussed in our today's lecture, and I hope that you have understand the fundamental concepts of the magnetic circuit, magnetic field, MMF, permeance, the topology, your definitions which are to be related with that magnetic circuits. We have discussed in the today's lecture, and I hope that you understand the today's lecture. And at the last, please don't forget to subscribe my YouTube channel Shoaib by Dayo for more informative videos related to the electrical engineering area. Thank you.